we were doing the standard error of the estimate, right? But conceptually, it's the same thing. We're taking some difference here between an observed value and hypothesized value. We're dividing it by some standard deviation or standard error measure. And we're still using the same distribution here, right? We're just substituting in slightly different terms here for these. But conceptually, it's the exact same thing, and it works the exact same way. Okay? As long as your sample size is large enough, as long as we can assume some idea of normality, right? If we're dealing with very small samples from very weird distributions, we can't do it. But as I showed you on that top 10 slide, that's not a problem if you have a sample size of 30. We're always going to have some underlying distribution for us that's going to be acceptable. Okay, so this is what we basically proved here. So here's our sample of 30. This area was only 42%, but the same range here. If you have a larger sample, now the area is 69%. So a 69% chance of getting our observed values. And I think it's the last slide I have in this case. Other sampling methods, let me just put them all up here. Stratified random sample. So again, if you had a large employee database and for some reason, let's say you found it unyieldy to contact all your employees, what if you just listed them in alphabetical order? Let's say you have 1,000 employees and you only wanted to sample 100, pick every 10th one, right? The stratified, that was systematic random sampling I was just talking about, right? Just take every nth or kth one, right? If you want to sample your employees, you don't have to do all of them. Sort them out, alphabetically or randomly. And then just take every nth or kth one and you'll get a systematic random sample. Stratified, again, maybe there's some particular frame you want to use, like you're worried about a particular type of department or a particular type of employees or a location or some industry or sub-industry, right? Maybe that's how you should focus your sample, is on that particular frame. Okay, cluster sampling. I know they do this in the like census bureaus from time to time. You know, we sort of think they're taking a complete census of the population, but they're actually sort of sampling, clusters and blocks and things like that. Maybe that has some relevance here. Convenience sampling. Again, I'd be real careful using these in true statistical analysis. You don't want to just contact your friends, people you know, right? Or people you know who are going to answer in a certain way. But that's not really statistics and probability. It's easy, right? And this last one, I don't know about that. I guess there's room for that in some worlds. You're going to ask, let the experts sort of choose the most representative people in the sample. Again, in politics, you sort of see this when you see the presidential candidates on stage, and the group of people behind them, they're trying to show that they're a representative group of the underlying population, right? We've got males, females, all ethnicities, all ages, and whatnot. They did this with some sort of convenient sampling. They didn't just randomly put people on that stage, right? They used some expert judgment to choose who's going to be in that sample of people behind the candidate, right, when they're on TV. So, what are you really going to do? Stratified random sampling, again, if you're really worried about your particular business, maybe it's a department, industry, something like that, that's okay to really focus your sampling frame on that. Or cluster sampling, right? Maybe it's just easier to go and sample everybody in this group rather than go to 20 different groups and sample 2 different people, right? If you think that's representative, that cluster is representative of the overall population, that's fine. That makes your job easier. Systematic sampling, that's probably the easiest way. If you've got a list of all your employees and you don't want to send them all an email or bring them all in, stratified random sample. You can randomize your list. I don't know why you wouldn't just get a random sample if you left it alphabetically and shows every kth one. Is there some difference about people's names? Nah, you wouldn't think so. So try and do something random. The real world, random, if you do something that involves random, I think you have your butt covered at that point. If you weren't putting friends of yours in the sample or people who you knew were going to answer in a certain way. As long as you've got some notion of random to it, I think you're going to be good. Okay. Why don't we take another break and then we'll get into the next chapter of the day. And we're going to compute some more stats. And again, this is where we're going to build 3 templates. Okay, so make sure that I think they're in your textbook. They show you how to build them, but I'm going to have you literally go through and build them so you have them when it comes time to do your midterms and your finals. If you save your templates, honest to God, I've even used this for my first class prep. I had a statistics question, and I realized the easiest way to answer it was to go into my EMBA prep, and I dug out one of these templates, and I just filled in the numbers in the template and got my answer rather than running a more difficult test. So these things are kind of helpful, okay? So let's take a break, and we'll come back and we'll start on these templates and more stats. Chapter 9. We're doing chapter 9, not chapter 8.
Is there any more?
Chelsea, give me more.
Yeah, I didn't last long either.
We didn't have enough evidence.
To eat or to play?
Tissue.
It would be her.
Yeah, we're going to do another template. There's 3 of them. Yeah, I've got the old text. Well, I'm sure he'll say. I'm not going to worry about it.
Chelsea, do you have self-control?
No.
No.
There's none.
Am I the only one?
And I'm easily influenced.
I mean, you're
Did you do the marshmallow thing when you were a kid? What, are you recording this?
Oh, peanut butter and chocolate.
If it was
I
anything else.
I thought Emerson leaves, so I started recording.
What's that?
You're not leaving me, I'll start recording it for you. Thank you.
Who's hurrying?
I'm okay.
Did you think you had an emergency?
Yeah. But it's good. We're good. We're fine.
Gotcha.
I like that you slowly turned around now. I appreciate that.
All right, see if you can go to Google.
Where are you going to write your paper? You can stay here? I got to write the paper. If I leave, I probably won't get enough. I'm swing by afterwards and help decorate. I need to go to my storage and I got a bunch of stuff.
I would know. We did a lot of time.
Yeah, see, that's not going to help me get this shit done. Because as you probably know, I'm not a nice person.
Yeah, that's true.
Like 11 o'clock comes and I'm like, yeah, 11 would be late for me.
I can believe you at 3. That's how you pull it.
Do it.
I don't know.
That's true. I hear that from a lot of people, but I have to have sleep. So, right, so I'm going to stay here probably until 7:30.
So far away. We live so far away. Yeah, right. Hey, we have a book that you. You're so funny. Look at you.
And look, all.
I actually did homework for you. Definitely for you. I was doing homework on your guest bed.
He goes, oh my God, I have to make the band and everything because I knew Amber was coming over.
I'm like, I will just.
I said, it's just Amber.
And then I got high for a little bit.
What?
Is that hot?
Yeah, there's like all these fumes going on in the cabinet, and I was like, and all of a sudden I was like, I'm like doing that guy.
You can define that over
I'm
a
like,
lot.
it's not me. He said Amber. I'm good.
Chelsea, I hope you're good with all this.
And then Dave like texted me later. He was like, I'm awake, and I'm thinking to myself, she probably slept longer because it was you.
Thank you so much.
What were you out there?
Yeah, I know. Oh my God. I know that it was.
Next time he's messing around with fumes, call me.
Okay. my phone? I can't believe
I'm
that.
trying
Oh,
to-
it works
trying to
so,
work
you know. Look, you put another crack in it.
Trying to bring it down.
You know the number of cracks. I do. Look, there's a new one, right?
No. So funny.
Okay, so I'm doing this exercise with my friends, and so every day you're doing so I missed yesterday, so I told her I'll be caught up to it. I'll do 2 days. And yesterday, no, I love it. We've been doing it for over 2 days now. Yeah, it's great. Yeah, now I'm going to put a little bit. But I said, so I'm doing day 23. She says back day 22. We could do every day. I have to do another day. I'm like, I know. That's how I'm getting that's perfect. Every day off. I know, goofball. You really need to do that next time. That's what I have, actually. There's simple exercises. Oh, I don't do it. But so like day 19 is 21. And oh, it's not bad. Super easy. So then we do cycle back around. But it's in the middle of the month. November 1st, we're starting. And then we're going to start. I do too. It's kind of cool. I know, I told Toma I'd do it. I'm holding onto my phone.
All right, you ready for another round?
Yeah.
To do this faster now.
You didn't end it though, did you go?
Yeah, I did.
I don't even know how to play. It's not a game.
I didn't either
Show
until
me.
she, let me get my phone.
I tried and I failed. My little ball, like, yeah, exactly. Isn't that a problem?
My phone's in my pocket. Dang it. Ready? Go ahead.
Take your
I
phone in your
did.
pocket.
Oh, wait, Chelsea's. That's so much fun.
Here, just play with everybody. It's fine.
Hey, is this Chelsea? She did go.
Are you playing beer pong?
Yeah.
Yeah, how do you play?
You go
You gotta get down
Wait,
on
come
that,
on.
don't you?
You're such a meanie. You guys are all so. Ooh, that's a pretty cover page.
Wait, you don't like that? No, but I read it. I'm like, yes. What is it with you iPhone people? You're so
Yeah.
Not even
snob.
figure it out.
I didn't play it.
I don't know how to play.
And then you find
Really
your
don't
iPhone.
play
beer
pong like a year ago.
Whatever.
The real beer pong?
The real beer pong.
In
real life?
Do you have a ping pong table at your place?
Well, we're gonna have a beer pong table.
There you go.
We don't have a ping pong table, but we have a beer pong.
Oh my gosh, you're.
You bought one already?
Of course.
Got what?
You're playing beer pong.
How do I do that?
Not me.
Beer pong on
On
computer?
the phones. If you have an iPhone, apparently you play beer pong.
Yeah.
I know.
Yeah.
See what you're missing out on?
Beer
I
pong.
still have not doing my iPhone.
You're like, she's all,
I did it. Do my
Yeah.
I didn't rescind it, I just, it looked like it had two phones.
Oh, I just thought you won. Get offended.
Here we go.
It actually wasn't.
Lisa, what time's your party tomorrow?
Around 6:30ish.
Is it like a question? Question?
It is. I put it on the Google Calendar. Can you guys make it?
Yeah, I've been so crazy. I didn't even ask.
Yeah, either that. Well, I think Dave wants me to get there first. Yeah, so like as long as I'm like 5 minutes before you guys.
Everyone else.
Oh, there you go. I'll see if I can make that happen. This is Shelly will be coming from down there. Exactly.
Yeah.
I know exactly. We have extra beds, extra mattresses.
Yeah.
So, I have a husband. Babysitters? Oh, you know, I actually thought about that. Isn't that funny? Well, is your wife going to come?
I'm texting her. I would like her to.
I hope so. I would like to do so.
Yeah.
I got all the girl players.
If you want to bring something, bring something. If you don't. Anything. It's open. Wide open. You can bring like a rocking chair. No. That's okay. We can handle it. You're right. I guess I should have qualified that. Although we will have trash cans, big ones. And recycle bins. And places for your tabs.
Oh, of course, so you have a little bit.
Yes, yeah.
That was my ride home last Friday.
Nice.
So work, home, could have just gone that, but I went down. So from there to there is gravel.
Oh, really?
Yeah.
So how are you liking the new bike?
I love it.
Oh, that's so cool.
Yeah.
I was talking to somebody the other day about those maps, and I was like, oh my god,
Okay.
I love it. So
I got it.
yeah.
I saw your Facebook posting.
That's where I live. That's where I work. So instead of going there, I went down, caught the 15, went to Jean, up to Good Springs, over there, Sandy Valley, and from somewhere about here to here, 16 miles, but it's gravel.
So how long does that route take?
Oh, that's
That was,
goes by.
2 hours, 8 minutes, 106 miles. So instead of 13-mile road, I made 106.
That's the way to do it.
Where'd you cross over at? Like an actual normal ride.
Yeah, so just jumped on the 15 there. Down here too.
My bike is so fast.
And
So I wonder if I could keep my bike on the side.
yeah,
And then
yeah, so
Yeah, that's
so
what
going
I'm
through
thinking.
Good Springs through here, this is real fun, but yeah. From actually about here, it was gravel,
Did you send your?
up
Yeah,
to
I did.
here was
Will you want
gravel.
me to text it to you?
And then I just went back up over the hump. When I got down here, I went through Red Rock. Yeah, that's,
Yeah.
yeah, well, this is the road to Pahrump.
I know this.
Yeah, so there's Pahrump right there.
Oh, the road.
Yeah.
I haven't
But from
seen
here,
it yet,
from
but-
about here to here, this is all gravel road. So I just went back over the hump, come back in, and Blue Diamond, I just went around and went through Red Rock and then headed home. So instead of going from there to there, I went
Yeah,
all the way
I
around.
And we just go
that way.
Yeah, it is.
Yeah, that's.
That's Sean.
And
That's what
there was the elevation problem.
she was doing all that.
So a high of 8,500 feet, 5,500 feet. This is Pahrump. That's probably Red Rock. This was Sandy Valley. Yeah.
And that's what a lot of people say there.
Yes, stunning.
I think that'll be perfect. I know, I'm looking forward to it.
Will you get the tab?
Yeah, I thought Amber was going to leave, so I fired this up so she could catch the rest of the show. What?
You took your time off.
I know, put them in the,
Oh, you did? Thank
Video,
you.
yeah.
All right. You guys, I love this.
when you see my wife tomorrow, make sure I can be trained. Okay, point that out, okay?
Maybe it's in her presentation. Should I
Nice,
talk to
you
her
go.
about
It might be. She's got some biases.
it? You microaggressions.
You, yes. Shit, I'm recording this.
Oh,
Lisa, I see a ribbon in there with a tablet.
I knew I
was
am
that
like
you?
this person. You took it off. You are awesome.
Say hi to the class.
I'm saying,
That's good.
Say hi.
Hi.
Chapter 9, this is hypothesis testing. And actually, this is what you've been doing sort of all along with these formulas. Right now, we're just going to formalize it a little bit.
Chapter
Our
9.
hypothesis test. So here's our learning objectives. Right, we're going to teach you how to develop these null and alternative hypotheses. Type 1 and type 2 errors. We're going to talk about type 1 errors, not type 2. We're going to do this when the standard deviation is known and unknown, and we're also going to do it for the population proportion. So what this means is we're going to develop a template for each of these last 3 items. So once you have that template, you can literally just throw your data into the template, and it will spit out your answer. Okay, if that's the right kind of test. So if you don't know what the standard deviation is, that's one kind of test. If you're dealing with a population proportion, that's another test, a different template. And when sigma is known, then this is the third different template. We're literally going to build all 3 templates with this example here today. And I think these are in your book. Again, I'm on a different version than you guys are, but I'm almost certain that the textbook is going to show you how to build these templates. We're just going to do it here, and we'll explain it as we go along. So your first task is sort of figure out, right, how do you set up the null and how do you set up the alternative hypotheses? The one is just the opposite of the other. It's the inverse of the other, if you Okay, and here's some helpful hints on how you can go about doing this. Let's look at the second one here. The null hypothesis, we call it H sub O, is the tentative assumption about a population parameter. Okay, so this is sort of what we're assuming. And the alternative is the opposite of that. And we're going to have to figure out how do we do this when we have actual data. But you want to set up your hypotheses such that when you reject the null, that it's actually giving you this alternative hypothesis. This is what you want to be able to prove. You don't want to prove the null. You really want to prove the alternative. Okay? So the null is something we're trying to reject, in essence. We're trying to set up our hypothesis so it's rejectable, it's testable, and we can reject it. We can collect data, confront that with a statistical test, and we can now say with certainty, oh, we can reject that because our evidence shows that the alternative is true. Okay? So this can get a bit confusing at times, and I'll tell you what, even Matt and I had some differences of opinion on this. I taught it one way in class, and he tutored it a different way. And frankly, I think in the example we were working on, I think Matt was right. He had a better, his way of doing it was a bit better than mine. He's an economist. I'm a management guy, right? Looking for the easiest path forward. But so anyway, this is not a big deal. We're going to show you how to do it. And here's one of the guidelines, right? Testing a research hypothesis, or you're testing the validity of some consumer claim. Okay? If it's a true research hypothesis, like the kind of stuff I do, we're really looking to kind of reject it. We really want to prove that these differences in these means are in fact significantly different. Okay? So the research hypothesis should be expressed as the alternative hypothesis, right? And the H sub O is just something you're testing, and you're hoping that you're going to be able to reject it, confront it with actual data, and then reject it. Testing the validity of a claim, again, the comment here is you usually give the manufacturer, the company, the benefit of the doubt. So we state that claim of theirs as the null. We're just going to assume they're right. So the example coming up is, this company produces cans of coffee with 3 pounds of coffee per can. Well, we're just going to assume that's true, and we're going to go collect data and see if we can in fact prove that that's not true. Okay, if we can now prove it's not true, we can go to the company and go, hey, you're bullshitting us. There's only 2.5 pounds of data or coffee in these cans. Okay, so when it comes to some claim that some manufacturer's made, we're going to sort of set that up as the null, and then when you collect data, you can confront that claim and decide whether it's true or false. Right? You're actually hoping, not hoping, but if you're testing that and you get a different result than the mean, you can now claim that that is in fact false. Okay, so that's, as far as help and guidelines, when do you set them up one way or the other? I think this is the best guidelines I've come across. Think about from the perspective, is this some claim that a manufacturer is making? If so, we'll set that claim up as the null. But if it's true research hypothesis, we're really going to sort of do the opposite. The research hypothesis is going to be set up as the alternative hypothesis. Okay, something, again, we want to confront with data and see if it's really different. So, like, again, back in the experiments I do, we get 2 groups of subjects. We give one of them a treatment, with partial information. We may give the other group full information. And the question is, did full information allow you to make better decisions than partial information? Well, that's what we're trying to prove. So what do? We set it up. We set our hypothesis up as, no, there's no difference. Those means are going to be exactly the same. Then we confront that with actual data, and if we do get differences, now we can conclude with statistical evidence that my information actually mattered in the outcome of the experiment. Okay? So this is what we're trying to prove. Again, the research hypothesis is expressed as the alternative here. We're actually, hoping that we do get it, not hoping, but we're expecting maybe we will get a difference in these means when we're comparing our samples in the research. So this pretty much sums it all up here, right? You could have a one-tailed lower test, you could have a one-tailed upper test that's going to look like this, or you can simply have a two-tailed test. This is what I was just describing with the experiment with sort of information. Are those means equal? Well, alternative hypothesis, no, they're not equal. That this information that we gave this one group actually allowed them to make better decisions than the other group. So we would get data and we would be able to say, I'm rejecting this. Those means, those performance means are in fact not equal, they're different. So I've got data that proves that, okay? You're not gonna get in any trouble with these two tails, it's pretty straightforward. Where it gets a little bit hinky is a one-tailed test, whether it's upper or whether it's lower tail. But honestly, if you use a little bit of common sense and think your way through it, I doubt it's ever gonna be much of an issue for it. But again, Matt, I think Matt has some pretty good insights on this. So if I can't clear it up with you, hopefully Matt will, and we're not going to be different in our approaches in the future. The first bullet point says the equality part as always appears in the null. What does that mean? Notice that this says greater than or equal to, less than, not equal to, right? Less than or equal to, greater than. Equal to, not equal to. Again, where does this come from? Legacy. This is just the way it's always been. And in the real world of statistics, it should matter not. It really shouldn't make a difference whatsoever where you have that equality sign, because if you remember from our first weekend together, I was really claiming that if you have this distribution, there's no such thing as getting this exact value. Right? You just if you have this continuous distribution of numbers, you're asking a value here. Let's say it's 2.5. It's not just 2.5. It's 2.5 forever. Okay, and your chance of you getting that exact observation to the nth decimal point is almost nil. Okay, but again, it really doesn't matter where this equality sign is, other than this is the way we've always done it in statistics. So when you're setting up your null hypothesis, we're always going to list it as this. It's either greater than or equal to or less than or equal to, if you're doing one of these one-tailed tests. Okay? One-tailed lower test. Well, how might you remember this? Well, for me, I like to remember this as the alternative, sign is really pointing to the sign of the tail, right? The alternative less than or equal to is pointing to the lower tail. The alternative greater than or equal to is pointing to the upper tail. Okay, and in this, it doesn't matter because we're dealing with both tails of the distribution. We're really focusing on the central part. And anything in either tail here would allow us to either accept or reject the hypothesis. So we get an observation, it's way out in the tail. Doesn't matter if it's in the upper tail or the lower tail, we're going to reject. Okay, we're going to reject the null hypothesis. So my comment here is use these two slides to formulate the null and alternative hypotheses. Right? One-tail test tends to be a little bit more confusing than two-tail tests because you have to worry about the direction of the test. I kind of claim that it's common sense. Once you sort of see them, think about them a little bit, it's pretty straightforward which test you really want to use when it comes to the one-tail, lower tail, or upper tail. The two-tail test is absolutely straightforward, right? Because we're not talking about any particular tail. We're talking about whether or not we're getting sort of quality here in some mean, some hypothesized mean versus some actual mean. So there's some practice. You guys take a read and tell me what the answer is here. So we're trying to set up the null hypothesis and the alternative hypothesis. Okay? And if you're already lost, let's just pause and think about it for a minute. Okay? Here's our mean distribution. Okay? We're saying it's around 12 minutes, right? This is sort of what we're talking about here, right? That we're getting a mean time of 12 minutes or less. So where on this scale would we reject that hypothesis? Would we reject it over here or over here? Over here, right? If we get some observation out here, we're going to say, hey, that's not less than 12 minutes. It doesn't matter how much less than 12 minutes your actual observation is, right? You're never going to reject the null hypothesis. So what we're saying is we're gonna reject this if we get an observation out here in this table, right? That's what we're worried about. We're going to sample. We're going to compute some sample mean, right? We're going to collect some data from this EMC hospital responders, and we're going to see truly what the response time was, and we're going to try and discover, is it in fact less than 12 minutes?
Question, wouldn't you reject anything above 12 minutes, not just the tail, because you want it to be below, or are you?
No, the thing is, right, what if your answer comes out to be, 12.01? No, reject that, right? That's close enough. Remember, there's variance and variability in our sample, right? Maybe we got a funky sample that wasn't quite right, right? For us to be able to really reject, we want to make sure it's way out here. It's statistically significantly different than 12, right? 12.01, yeah, that's not statistically significant. At some point out here, though, it is, right? At some point out there, that's going to be huge. So again, if you think about our research hypothesis here, right? This is what we're really searching for, right? We're going to reject this notion. We're going to give them the benefit of the doubt here, right? Yeah, your service time is in fact less than 12. But if we get this, if we get an observation that's greater than 12, at some point we're going to reject it. So again, how do you set them up? Again, I always think about, what's the statistical test going to look like? And I know it's going to look like something like this. Here's the 12, and we're sort of asking, well, how far out here before we would say, hey, that's a lot more than 12? Well, 12.01 isn't going to do it. Maybe 12.2. Who knows what it's going to be until we actually compute it. But I know the test is going to be out here in this direction for this particular problem. So what is that? Well, here's the alternative. The mean is greater than or equal to 12. So I sort of knew what the alternative hypothesis was just by thinking about the mean and where the actual test is going to be. Okay? Does everybody get that? How we concluded that? Okay, clearly this is the goal. Okay, and before we're going to claim that this isn't true, we're going to give them the benefit of the doubt, right? This company is claiming that, or hoping that they get there in 12 minutes or less. We're going to give the benefit of the doubt. But our actual test, whether or not that's true or false, is going to be if we get a result out here, which is H sub A is the mean is greater than or equal to 12, just like the test would probably, could possibly show you. Okay? Here's another one. Let's try this one. So, what's our H sub O and H sub A again? H sub O and H sub A. Right? I'm a little uncertain. What am I thinking of? I'm going to think about it conceptually. Well, here's the mean of 24 miles per gallon. what's it going to take me to really prove to somebody that this system is working, right? That you're getting better gas mileage. Well, that proof is going to lie out here again somewhere, right? We're going to collect a sample, and we're going to try and understand, right? Do you really have evidence to show that this new process is generating miles per gallon greater than 24? Right? And think of the other side of it. What if you got an observation down here that was 22? Well, that's not going to prove anything, right? That's certainly not going to help your case that this fuel injection system has actually increased the miles per gallon. So again, knowing that that the statistical test as far as acceptance rejection, that the H of A is going to be out here, right? That's what we're going to get again. Same thing as before, right? Our statistical test to reject that conclusion is going to live out here. So we know we're dealing with this one-tailed test. And again, the H of A is kind of, pointing to the tail of the statistical test. Right? So that's what I would look at, right? When I try to answer these questions, I would look at that and say, look at my distribution, and say, well, the alternative I know has to be something about the mean being greater than or equal to 24, because that's the actual test that's going to determine whether or not this is true. So the null hypothesis must be sort of the opposite of that. So it's less than or equal to 24. Okay, that's really, these don't come to me automatically. I always think of them as the actual test, and I kind of work back from that. I know where, either this tail is going to reject it or that tail is going to reject it, and that's really pointing to the alternative hypothesis. Okay, so type 1, type 2 errors. First of all, let me just get ahead of myself here. You can only make 2 types of errors, okay? Notice that we have this correct decision here across the diagonal. So, and I'm going to call this accept and reject. Matt's probably going to call it fail to reject, not accept, okay? But this is just a difference. I think it makes more sense intuitively trying to understand this, but there's a fine line that some economists will draw. It's not that you're accepting, it's you're failing to reject it. Isn't that accepting? You got a binary world, you either accept it or reject it, right? But some economists like to draw a very fine line. They like to say fail to reject. I like to call it accept. Okay, so we've got accept and reject is what your conclusion is, and what's actually true here, right? Was H sub O true or was it false? Well, if you accept it and it's true, you made the right decision. If you reject it and it's false, you made the right decision. Where you make your type 1 error is when you reject the hypothesis that's true. Okay, if you reject the hypothesis, it actually turns out to be true, you made a type 1 error. Well, this is pretty easy to interpret. What is a type 1 error? It's the same thing as a level of significance. So if you do a statistical test and you're doing something with 95%, it's true, your level of significance is the 5%, that's the probability of the error, it's 5%. It's your level of significance. Okay, straightforward. It's one and the same thing here. Type 2 error, I'm not even going to get into that. I compute statistics, in every paper I do. I've never even had to report a type 2 error. Right, we've got ways of doing this, there's ways to compute it, but trust me, this is for a whole other statistics class. This is not for our class. And I really don't think you're going to encounter it much in the future unless you become really stats jocks and go forward. Okay, but that's what a type 2 error is. It's when you accept when you accept the null hypothesis when in fact it's wrong. Right? You made a mistake. It's called a type 2 error. But this is the one we're talking about here. It's called a type 1 error. And what is it? It's simply the level of significance. So when we do tests, with 5%, alpha's 5%, 10%, 1%, that's the probability of making a type 1 error. It's that straightforward. It's one of the same things as significance level. Okay, so let me back up if I missed anything important here. Here it is, right? Type 1 error, rejecting 8 sub O when it's true. Probability of doing this is the same thing as your level of significance, alpha, here. And you get this reported to you in all sorts of statistical tests. It's going to be output. You don't have to worry about it. But again, let's just pass right there. This is for more advanced statistics classes and textbooks. We're not going to worry about it. P-value.
Bingo.
Okay, the p-value, right? This is saying it's anything we've been computing before. This is the probability of getting an observation out here. We call it p-value. It's a probability, right? It's the same exact probabilities we've been computing from the z-tables, right? We've been computing all of our statistical tests here. We're literally computing a p-value. And it's going to show you how likely it is to get an observation in this tail, or again down here in this tail. So if this is the test, right, this is going to be a lower tailed test. If you're looking for a value up here, this is the upper tail test. So what are the last two tests that we did? Were they lower tail, upper tail? Okay, we're gonna take a look at that. Okay, but that's, yeah, there's the symmetry here is really the same, right? You're looking at whether or not, you know, your observation is in this tail or is in that tail, and whether or not you're going to be able to accept or reject the null hypothesis here. Okay, there's nothing really that new in all of this. I should point out this. I see these things as one and the same, but you guys may not. P-value approach to one-tailed hypothesis testing. One way to determine whether or not this is significant is to compute the p-value. The other way to determine whether or not this is significant is to compute the critical value. And then I see these as one and the same thing, okay? Here you're computing these critical values, and we're saying, oh, if the observation is up in this tail, then it's significant. Or if it's down in this tail, it's significant. Where we draw this at our identical level of significance here. You might remember that. Alpha at 0.10 is minus 1.28. Alpha of 0.05 is 1.645, right? These are right out of our z-tables, things that we said you probably remember if you do this often enough. Right? These are the critical values. And now you compute an actual test statistic, and it tells you whether or not you're on this side or that side of the critical value. P-values and critical values, they're using the same information, they're getting at the exact same thing. It really determines your comfort level, how you like to do things, or maybe the particular problem you're solving in our textbook. But these approaches will yield the exact same thing. If you're doing a p-value, I kind of like the p-value because it's easier to compute, right? It tells you what the probability is. If you compare that to your level of significance, you know whether you have a result. But again, the critical value, it's the same thing. We're computing this critical value, and we're seeing, did we get an observation greater than that? We compute a critical value, did we get an observation less than that? So they're one and the same thing. Unfortunately, we're going to drag you through both of these methods just to show you how to do it. And again, we've got some templates that are going to answer both of these questions simultaneously, so it's not a big deal.
Is that a standard projection, or is that just, you just pick whatever you're talking about? It's like 0.05 on the top and 0.1 on the bottom, your standard.
No, just,
Levels, you're just picking a number.
no, I actually wanted to show you an alpha of 0.05. Right, this is like being 95% confident, right? If you get an answer over here, you're 95% confident. So that's what that alpha corresponds to. And this 0.10, again, that's just that z-value that puts 10% in the tail. If we wanted the 10% up here, it would be plus 1.28. It's just the z-value. So you know, knowing that you'd have to look up the z-value or literally compute this critical value, and then you're going to take your data, you're going to compute a critical value and see if you actually got more or less than that. But again, it's almost identical to the p-value approach. So again, here's the steps. Develop your null and alternative hypotheses. You have to specify your level of significance, right? You know, is it 5%? in this class and in almost everything I do, we always assume 5%. We want to make sure that if we get a difference in our experiments, that there's only a 5% chance that that's due to chance, that it's probably real. Those differences in the means are truly real. There's only a 5% chance of making that error. Okay? But if you're dealing with healthcare, you got our chiropractor over here. I mean, he may want to be more certain. You don't want to go messing with somebody when there's 1 in 20 chance. You're right. You might need it to be 99%. Or you might not even care. 5% too. 20% is good enough, right? But when you're dealing with people's health, right, you want to be more certain.
To pay their billions.
You pay their we have an adjusted p-value based on.
No pun intended.
So I mean, again, 5%. This is just sort of the industry standard to choose 5%. But again, if it's really important, you don't want to make a mistake, maybe you ought to use 1%. Right? Life's on the line, things like that. You might want to be absolutely, not absolutely, but more certain. So how do you do it? Like collect the sample data, use the value of the test statistic, and compute the p-value. Confront that p-value with your level of significance. That's going to tell you whether or not you're going to, accept or reject the hypothesis. Critical value approach. Use the value of significance to determine the critical value. Right? So we're using the same stuff. It's just, in one way, we're sort of using at the end of the test. And the other part, we're using data from the middle of the test. But we're doing the exact same thing here. Okay? And the critical value, we're going to compute this value. We're going to compute this value of significance, and then we're going to draw our line in our mental chart here, and we're going to figure out whether or not the test statistic really falls on which side of that line. So let's just try this. Again, here's the Hilltop coffee that I was talking about earlier about coffee, whether or not they had 3 pounds in the can. Give that a read. So here's my normal distribution with a mean of 3. Where are we going to find a conclusion to reject this hypothesis? Let's just assume that it's a one-tailed test for a minute, right? It would be okay with consumers if they got 3.5 pounds, right? Nobody would get on their case for that, but so we're going to assume this is, again, it says one-tailed test up there, but most of the, tell you what, most of the tests I ever run in the real world are two-tailed tests, but this is where a one-tailed test sort of comes into play. So down here, right, is where we're going to reject it, right? If we find an observation of, 3.5 pounds, well, we can't claim that they're cheapness, right? They're giving us more coffee. Where we're going to find some concern is whether if we get an observation down here. Okay, so now that I know that I'm interested in this particular tail, right, I now know that the alternative hypothesis, right, the inequality is kind of pointing to the lower tail. Okay, so there's our null and alternative hypotheses. You can do these tests without actually setting these up, but this is part of statistics. What's the level of significance? What is it? 0.01. And what's the test statistic? There you go. Well, think about it, right? We're talking about what's our observation is 2.92 minus 3. And what is our standard deviation / standard error? 0.18. What's our sample size?
36.
So that's what we're doing, right? That 0.18 is the standard deviation is assumed to be known. We're just making it easy for you. We really don't know what it is, right? We're just saying, oh, if you know what it is, then in fact, this is the formula we're going to use. So we give you the 0.18, but you're going to have to compute the test statistic. So now this is the test statistic. Okay? Hmm?
It's just the square root of the bottom, right? It's not the whole square root.
Oh, shit, what are they doing? Okay? So that is in fact our test statistic. Again, we're gonna, we're still use the Z table. And let me just ask you, I don't expect you to have an answer. Why are we using Z?
Because it's a population, sample population.
Because you're very close. Because we actually have a known value for the standard deviation. That's what it is. That's why we're using, what enables us to use the Z statistic. Okay, we're getting real close to building our templates here, but so here's our Z value. So what we're saying is that if we had this observation of 2.92 when the mean, the hypothesized mean is 30, the normal standard deviation is 18, we have a sample of 36, this becomes our Z value. And note this is the Z value. This is the 2.92 pounds, okay? But the actual Z value is minus 2.67, which is a little, given we're in the same scale here, I just want to point that out. That's not, we're testing this 2.92, but we got a Z value of 2.67. So what do we do next? Well, now we're going to compute the p-value. Again, how do we compute the p-value for this? Normal distribution, right? You can literally enter these values into the normal distribution function in Excel. Don't have it up here, right? But if you do, you would get a result of 0.0038, right? Or if you looked up your Z value in your textbook, if you looked up a Z value of minus 2.67, you would get a probability of 0.0038. So do we accept the null or reject the null? Reject it, right? The null hypothesis is everything was okay. Their coffee contains more than 3 pounds, right? The alternative hypothesis was that, oh no, it's less than 3 pounds. So because we got an observation way down here, right? Way down here, the probability of getting that is 0.0038. We're going to reject the null hypothesis. We're going to accept the alternative that, in fact, this company is not putting 3 pounds of coffee in the cans that they advertised that they were. Okay? Right? Here again, this is the whole point. The way you want to set it up this way, now you have statistical evidence you can confront the company with. Right? You can say, hey, look, I did my statistical test, and look, the chances of getting that, that result, sampling and opening 36 cans of coffee and weighing them and all that, right? This is the probability of getting a mean of 2.92 for a sample of 36. Right? That's what that mean was. It was 2.92 for a sample of 36.
So what does a 0.0038 versus a 0.01 mean? I mean, what is that? Like,
The 0.01, okay, that was our level of significance.
right. And so isn't that better than that? This is the 0.003.
It's less than that.
More accurate.
It's less than that, right? Our level of significance was really the Z value of 0.267. Right? Again, don't compare the 0.292 and the 0.267. This is pounds of coffee. This is a Z value. They just happen to be in a similar scale. Okay? So the probability of getting an observation out of sampling 36 cans of coffee, given the standard deviation of 0.18, okay, turned out to be 0.003. It's very unlikely that you would ever get this observation if the true mean was 3. If the true mean was 3 pounds of coffee, right, the chance of getting that observation is less than less than 0.3%, right, 0.003%. Okay? Okay, so this is the p-value approach, right? This is what we've been doing all along. We've been using our formulas, and we set up the null and alternative hypotheses. We computed that with our Excel function, our normal.dis, and we got a probability of 0.0038. So we would reject it, and we would claim that nope, right, they're not meeting the 3 pound claim per can.
So,
Critical value approach. Yeah, go ahead.
so if that was 0, then you would accept it.
If what was 0?
If the p-value was 0.
Your p-value, is that 0.003?
I would reject it. If the p-value was greater than or equal to 0.01, we would accept it,
Oh, gotcha.
right? The significance level, right, is telling us, right, we wanted a 1% chance, right? Wanted 1% down in this area and 99% up here.
Instead we got a 0.3.
And we got a 0.003 result. It's less than 1%, it's even less, I mean, it's less than 5%, it's less than 1%, right? It's very unlikely.
But we got it.
But we got it. And so therefore, something's probably wrong, right? They're advertising you're getting 3 pounds of coffee per can, and you're not. I mean, we have statistical evidence to claim that's not true, right? We sampled 36 cans, we got 2.92 pounds, and we're asking the question, well, was the sample size large enough, right? I mean, was this observation, this mean, right? This is the mean of all of those cans of coffee, right? We opened up and weighed every can of coffee, and we summed it up, we got this mean, and the manufacturer claimed there were 3 pounds. This is the hypothesized mean, right? This is what they're claiming is in the can. Our observation was that. So again, in our formula, this is sort of our X bar. This is sort of the hypothesized mean, if you will. And then what do? We divided this by some notion of standard deviation, which was, in fact, the standard error. So this was the standard error of the estimate, right? That's what we did. We divided this. Again, we took the difference, the 2.92 and the 3. We divided it by the standard error of the estimate. We said, well, how many standard errors is that away from the mean? Well, it turns out it's pretty far away from the mean, right? It's way out there.
We could actually go the opposite direction to find out how many pounds would be right at the 0.1% or 1%.
That's right.
And that would be like 2.99 pounds, but we're at 2.98, so we're way below. That's what we reject.
Yeah, you could actually, if you really wanted to be, like a shitty manufacturer, you want to say, what can I get away with here? You could actually work this backwards, right? You can sort of figure out, well, for a sample size of 36, we pretty much know what kind of a mean we have to get to be able to fail to reject the null hypothesis. So the consumer goods company couldn't come down our backs and say, hey, we did a test and that's what we got. We assume companies aren't acting like that. But.
You know the numbers kind of going like this.
Yeah, let's just do it. I need Excel to do that. But let's just have Excel. Let me open up an Excel file. Let's do it.
It's there.
Okay. So we're gonna do this test. Okay, we're gonna do the norm.this, so it's equals, then start to type norm, and we know that we're doing this norm.this, and I know we're doing a sample here, but that's not, we don't want this norm.s. We don't want the sample because we're dealing with
That's standard. We're not standardizing.
So anyway, here's this norm.dis, okay? So what's x bar? Again, x is always sort of the observation, right? It's It could be the sample mean, the single observation when we were dealing with this before. So this is our 2.9, 2.92, okay? And then the mean is 3. And the standard deviation, okay, well, I'm going to put it in as a formula here. What is it? It is, let me use my print, it is 8.18 divided by a square root of 36. Not sure why they're doing amounts of square root. That's
It usually doesn't inside your thing.
that's QRT.
It's QRT.
And get your.
Oh, there you go. Square root of 36.
Which one is that?
And then this is,
You missed a parenthesis.
yeah, what did I miss?
A parenthesis.
Second parenthesis.
After the 36. 2 parentheses after the 36.
That's it, thank you. Okay. I should wear my glasses.
Yeah, true. Can you put a 1 in there instead of true? That's what 1.
Yeah, mine's for one there. Dude. Instead of saying.
Sorry, that took so long. I have glasses, I could wear glasses. So, again, how did we get that? Again, there's the 0.003, right? This is what we had on the slides and everything. We did the normal dot dis, same formula we used last week, right? And we put in the values that we knew. Here's the 2.92, the mean was 30. And the standard deviation, well, in this case, we're using the standard error. So I could have computed it, right? That would have been a lot easier than trying to do a formula inside of a formula. But yeah, you can do that, right? I took the square root of 36. A 0.18 divided by the square root is 36. And then true, and that gave us the probability, just like it did 2 weeks ago, of this. So that's how we get the p-value for that test.
Can you go back to your slide for a second, your picture? So does that relate to the graph? So in that picture, you've got your 0.038 is that area. So is the 0.01 bigger than that? And so your observation fell within that? Or I'm trying to understand the
Okay.
0.01.
Our significance level was 0.01. Okay, so if we get a value that's beyond, right, less than our level of significance, then we know it's significant. We were allowing for a 1% chance, and what did we get? We got something that's very unlikely. It's less than 1%. It's 0.0038%. I shouldn't say 0.03, but it's 0.0038. Right, that's not a percent.
So if it came up at
If the value was-
0.012, then that would have been okay.
That would have been okay.
Because that means that every sample, or at least all of those samples, were greater than that line.
It would have been, let's just,
The mean of the samples.
do one better here. What if we would only have a sample size of 8? Now would we accept or reject the hypothesis? We'd accept it. Because why? Our probability of being down here is 10%. Our screen was 1%, right? We said we're gonna reject it if it's less than 1%. Okay? So again, this value, it depends on not only your true sample that you drew, but also depended on your sample size. Right? And if we had a very small sample, we would not be able to be able to reject this claim, and the coffee maker would get off scot-free.
You don't have enough samples to be able to catch that.
Right, right. And so the coffee maker, if you want to lie in statistics, right? Here's a way to lie in statistics. You're the coffee maker, right? You can claim, well, I sampled, 8 cans of coffee, and our result was not significant. We still got the same 292, but it's not significant. But again, for the 36, right, you would in fact say that is significant.
Does your 30 have a relation in here, like 30 is your number again, where it's your minimum sample?
Well, let's see what 30 would have done. We're always sort of claiming that 30 is a good number. Let's see what 30 would have done here. Still significant, right? But you get smaller samples, and you're going to start to show that there's just too much variance. That your sample size is just too wide. You can't really prove anything, right? Nothing significant if you have huge sample sizes. So that's the relationship, okay? Here's a p-value. Here's a critical value test. Again, it's sort of one and the same thing. We're just doing it from a slightly different perspective here. Now here we're going to determine that critical value, right? At what point are we going to reject this hypothesis? So again, you could look this up, and our critical value would be 2.33. How would we get that critical value? Well, we can go back to the Excel functions, and this would be the normal inverse. What's the probability of getting a, what was it, 1%? 1% from a mean of 3 and a standard deviation of, oh crap, here we go again. 0.18 divided by this. That's it. You get that 2.93. Yes, sir. Anyway, not worried about that.
You need to make that 1.01 calculate the percent conversion. No problem. Yeah, but make that 1.
Oh, so 1% instead
Right
of
now
0.1%.
you're 0.00.
No, that's a good thought. I'm not certain when I did that. Boy,
Is the mean 3 or is it 2.33? The question on the slide is
2.92.
2.33.
all right, I'm not gonna worry about that. Again, p-value. I did something wrong on the sheet here, right? What you're doing is you're actually looking for this alpha value. Not quite sure why it didn't come out 0.01, but you get this. You actually get this line that says, okay, if you get a critical value of less than minus 0.233, then you reject it. And then we actually compute our critical value. We got 2.67 because that's less than minus 2.33, you reject it. Yeah, it's the same thing. We're just whether or not you're doing it with a p-value or whether or not you're doing it with this critical value approach. We're doing one and the same thing. If you want to know where to get that 2.33, I'm not certain why this is an issue, but you could look up your z tables and look up 1% for your z table, and that's what you would get for the critical value. Oops. Okay, I'm behind. We got one more example here. Let's see if we can do this. Again, p-value and critical value approaches. Let's see if we can come up with the hypotheses. Conduct the test. See if I understand what we're looking for here. So this is the way we should be thinking of it, right? We're claiming that the response time is 12 minutes. Our actual observation was 13.25. We're trying to understand, right, is that significant to reject the hypothesis that calls are answered in an average of 12 minutes? So again, this is the area, right? We're actually going to conduct the test, and if we find out that this is in the significant region here, then we're going to reject the null hypothesis. We're going to accept the alternative. So we're going to develop the hypotheses. Again, the alternative, right? This is where I like to remember it, right? The alternative hypothesis, the one-tail test, this is pointing to the tail that is going to determine the test itself. That's fairly straightforward. So the alternative, the null hypothesis is just the opposite of that. So we've developed the hypotheses. What's the level of significance? 0.05. We're going to compute, again, the test statistic. Yeah, there it is, just like we've done before. Take our observation of 3.25, subtract the mean from that of 12, and we're dividing it by our standard error. 3.2 was in this problem somewhere. The standard deviation is believed to be 3.2. In the overall population, we took a sample size of 40, so we computed a test statistic of 2.47. Okay? Now, if you remember your critical values and things like that, yeah, we know that's way out here in the tail, right? 5% level of significance, isn't that 1.96? Isn't that our t-value or our z-value of 1.96? So we know that's way out there, and we'll do the test. P-value approach, well, how do you do it? We're going to, for the z of 2.47, our probability is 0.9932. And again, we're interested in this area, so we subtract that from 1, and we get a probability of 0.0068. So do we accept the null or reject the null? We reject the null, right? We're way out here. The null was saying that, oh no, you're less than 12, right? You're less than 12 with a little bit of error out here, right? Well, our value proved that, no, we're way out here. So we're going to basically accept the alternative hypothesis, okay? That this did not happen by chance, right? This happened because we're not meeting that goal of 12 minutes at all, okay? So we reject it. You know, if the p-value is less than that, it is less than that. So we can, in fact, do it. They are not meeting their goal. And if you want to do the critical value approach, I was wrong. It's a one-tailed test. It's not 1.96. I forgot. The critical value is 1.64. Again, you can look that up in your z-tables, right? That's the critical value that you would use to determine whether or not to accept or reject the null. We already computed our critical value, and what do we get for a critical value? We got a critical value of 2.47. Okay, so we would accept it if the critical value is less than 1.64, but since it's greater than 1.64, same thing. We reject the null hypothesis, we accept the alternative. The same thing, just what do you want? What would you rather compute? The p-value, or would you rather compute, you know, the test statistics and go after it that way? They're going to give you the exact same answer in every case.
Figured out why we couldn't get on the previous slide. Why we didn't have the answer right. Yeah. When we're doing that critical value approach, you put that into Excel, you assume a standard
distribution curve.
Standardized curve. So you were not, and we use the S more dot S dot inverse.
That was hard. Yeah, there was some. I shouldn't do some of these things on the fly. You know, when I have to run statistical tests, I love to use Excel, but the problem is I usually have to use some other packages like SPSS or SAS because it's just not quite powerful enough for academic reasons. But honestly, I'm very impressed with Excel and its ability to compute statistics. I mean, I think this is the right way to go with you guys. And even for me, I would prefer to use Excel. Sometimes I can't, so I don't get to use it as often as I would like. I have to use other statistical packages. So again, this is sort of a summary of the p-value approach, it's the critical value approach. They're going to yield the exact same answers. So here's another example. Let's do this. We're going to open up golf test. What's that? Oh, golf.
Yeah.
Are you a golfer, Eric? I do enjoy it. So this is our first template, okay? And I'm going to get you guys, here's the data, we all have the same data. Okay, I've just added some line items here and I shaded them. We're basically going to compute, put a formula in here for every cell, okay? And when we're done, we could literally replace this data with any other data and we're still going to get our statistical test. So that's the sort of the benefit of doing this template, okay? Once we build this template, that data over there in yards, you could replace that with any other continuous variable, not gender, male, female, but any other number, okay? We could use any other kind of data we have, and this template would still give us the answer, okay? So there's your data, and mine has a few more line items, but let me just ask you guys to do the same thing. You don't have to have them in the exact same rows or anything like that. If you do have them in the same rows, it'll be easier to follow along here, right? Like start this in row 4, sample size, sample mean. I don't know why I have a blank, just to be neat, I guess. That's probably the way the textbook did it. You don't have to shade that, but let's put the formulas in. You guys are doing this. Let's put a formula in for sample size. What is that formula? Okay, it's count, right? And the other sort of, so we're going to say equals count. And we could paint up that range. Bingo! Or, let me show you another trick. And I honestly got to learn this teaching this class.
Call my column, man.
Yeah. A.
You can just click on the column. Click on it.
Oh, really? Okay. You guys know better than I. There you go. Okay. If you do A colon A, look what it does. It literally, I didn't have to paint up anything, right? That's just a handy little way of referencing the entire column. And note too that it didn't use yards, right? So why is that? Well, if you look at the actual formula, why didn't it take yards? It's telling you this counts the number of cells that contain numbers. Okay? So you get to keep, if you want to put a heading over your next column of data, you can do the exact same thing, and your formula is still gonna be true. It's everything in that column, right? A colon A. What goes here? The sample mean.
Average.
Okay, we're going to do average. And then
Even an A column.
I didn't know you could do that, so I learned something new today myself. I thought you had to literally type in A colon A. Okay? Population standard deviation. Here's our STDs. Don't get any this weekend. Right. So here's our standard deviation, the sample. Right, that's the one we want, and we're going to paint that bad boy up there. TMI. Hypothesized value. Oh, so I'm sorry here. That's not wrong. The reason I have these shaded in green, I shaded in green to remind myself. You see how much good it is. You have to actually enter something in here, right? And that comes from the problem itself. So, what was the golf problem that we're trying to solve here, right? It says the hypothesized standard deviation, the population standard deviation is 12 yards. Everybody got that? 12 yards. Okay, so, well, I had to enter that. The hypothesized value is what? Hypothesized value is 295 yards. And we have to enter that as 295. So that's why I shaded them in mine, just to remind me that in the blues go formulas, and in the green cells we just have to enter something. So if you're running some other kind of statistical test, these formulas will be true, but you're going to have to enter the population standard deviation and some hypothesized value. So the standard error, enter the formula for the standard error. What is the formula for the standard error? What about that? Okay, I thought I'd show you that rather than drag you through it, right? The standard error is the standard deviation divided by the square root of n, right? That's what we've been doing all along here for the standard error, right? It's the standard deviation, right, divided by the square root of n. So there it is. Standard deviations in D7 divided by the square root of D4. Square root of n. The test statistic, no surprise, let's look at that. What is it? Just like the formulas we've been doing all day, right? It's the observation, the sample mean we observe, minus the hypothesized mean, 295, divided by the standard error, right? This is the formulas we've been computing all along and using today. So now we have it in the template.
So the hypothesized value is the hypothesized mean.
Right. The hypothesized mean was these golf balls fly 295 yards on average, right? Your drives go 295 yards there?
On average.
Ask him what the standard deviation is.
So, yeah, I guess they do these with golf machines, right? They have, these machines that actually swing just as hard every time, and they put the balls up and they measure and whatnot. The test statistic, we've already done that. Didn't we just do that? Yeah, okay. And then if, okay, we're sort of allowing for all possible tests here, right? Lower tail, upper tail, and two tail. We don't know what kind of a test we're doing here, but let's just do them for all. So the lower tail test, norm.s.distribution, we're taking, right, the test statistic here, and we're literally looking that up, right, from a normal distribution, right? We've got the test statistic, and that's normalized. So we're saying, okay, what's the probability of getting that? That's 0.93. Then the upper tail, okay, now we're over here in this tail. Okay, the formula is 1 minus that, right? Because we're looking at this area. So what we did 2 weeks ago, where we draw this line, if we just say normal dis, it's the area to the left. If we say 1 minus, it's the area to the right.
Backwards.
Okay, so now we have a p-value down there of 0.06, and then the p-value of the two-tailed test. And trust me, just copy that formula. I'll try and explain to you why it's 2 times the minimum. Okay. Because we don't know whether we're doing an upper tail or a lower tail test, only one of these makes sense. In this case, that doesn't make any sense. Okay, we really need to take the minimum of this. And then imagine that you're spreading this out into 2 different tails. Right? We're taking the minimum test, which is the real test here. We're spreading this out into 2 different tails. So that's sort of why we're multiplying it by 2. You spread it out into 2 different tails. Okay, so there's your formula. It's 2 times the minimum of those 2 cells. Okay, and if you do that, you now have the p-value for a 2-tailed test. So, yeah, this is supposed to be a generic template. We're not sure if we're doing a 1-tailed or 2-tailed or an upper tail or a lower tail test. We're just computing the statistics for every one of those tests. Now, if we're doing our golf ball question, right, well, what are we saying here? Let's just think about this, right? And the hypothesis was the mean was what, 295? And we got an observation of what? Go back to this. We wanted to know, here's our null hypothesis, whether or not it was equal to 295 or not equal to 295. So this is a two-tailed test. Okay, so now we're saying that anything out here or down here, if we get an observation in one of these tails, we're going to reject the null hypothesis that the mean is 295. We'll have proof that it's not 295. It's either way lower or way higher. Okay? So this problem basically told us that what our observation was over here somewhere. It was 297 something, right?
0.6.
0.6. Okay? So again, but the fact that it was a two-tailed test, we don't have to worry about this. We know that we're going to reject it if we get an observation in either tail. Okay? We know we're doing a two-tailed test, so we can easily go back to our two-tailed test. And do we accept the null or reject the null? Right.
Accepted on the two-tail and rejected on the
Minus.
Yeah, but we're not, again, we weren't really asked to do a one-tail
Is there a
test.
formula for the p-value?
What do you want to see?
The formula for the p-value of the lower test?
Okay, so again, this, hopefully, if you remember, what we were doing earlier, why this is the normal dot disk, right, for the one-tailed test. If it's a lower tail test, we're worried about stuff down here, right? Isn't that what, remember your Z table? Whatever you got, it told you the area to the left of the line. And in the upper tail test, it's for the area to the right of the line. Well, the Z only gives you this, so when you want to do an upper tail test, it's 1 minus that norm dot disk, okay? So the upper tail test, just like we're doing with the Z values, we're actually checking that. So again, these upper and lower doesn't make any sense for this because we knew we were doing a two-tailed test. We were just setting up this worksheet, so now you can put any data in it, okay? So everybody got it together, this actual template? Okay, again, you could literally take this template and you could just throw another column of data in there, and these formulas would self-correct and you'd get your answer. You still would have to decide yourself, am I looking for a lower, an upper, or a two-tailed test, right? But again, this problem that was given to us, we were looking at a two-tailed test, so the answer is right there. So we got formulas there. We have values here that you have to enter. That's why I shaded those green, and didn't even remind me when I saw them in my worksheet. But that is your first template, and the title is Hypothesis Test about a Population When You Know the Standard Deviation. Right? We knew the standard deviation because we actually had to enter it in the template. Okay? Everybody got the template? I want to give you one more before we go, but I'll go at any pace you want to go.
I have a question about the last one, the two-tail. How
Yeah.
do they look in the distribution? There's a little too fast for me.
Okay, the two-tailed test is we're basically saying, if you remember the 8 sub O, it's saying that the mean is equal to some hypothesized mean. Right? That's what this golf ball thing was all about. It's saying, well, we got a sample and it was 200, the hypothesized mean was 295, and our observation was 297.6 or something. So we're asking the question, is that significantly different? Well, the answer is no, right? It would be different if it was way out here in this tail or way out here in this tail. And what's the probability of this being true in a two-tailed test? Is 12%. Our significance level was, what, 5%?
Yes.
So we can't reject the null hypothesis. We have to accept the null hypothesis.
It's greater than 0.05.
Right, because it's greater than 0.05.
Okay, so the 12% of almost 13% is divided into like the details. So you have.
No,
Those are the probability areas. The tail.
right. I understand, right, that's the probability of the two-tailed test. Again, if you just specified your test that, that the level of significance was 0.05, okay, it's basically going to put 0.025% in this tail and 0.025% in that tail. So that's what we were really looking at here. Did we get something that was, less than a 2.5% chance in this tail? No, we did not. We got something, right? It was 12.5%.
What was the 12% be? Like almost like 6 on each side? 6% the other? Am I really confused?
No, you're not confused.
The probability for the p-value is based on your z. So if your z moves in closer to the middle, it goes up. So your probability of 0.12 is higher, you're closer to the mean.
So we're saying the probability of getting this, okay, is roughly, 12.5%. So that's not, that happens, right? It's a little bit higher than the 295, but it's not statistically significant, right? To be statistically significant, you would have to fall in one of these tails. There's a 2.5% chance of this tail and a 2.5% chance of that tail. If you like this alpha, right? This alpha at 0.05, and that's what the problem gave us. It said an alpha 0.05. Didn't we enter that somewhere? Yeah, we entered it in these formulas, right? No, we didn't. We didn't. We did not really have to enter it because, again, this is a standard template, so you're going to decide what your alpha value is, right? This is just going to report the statistics to you. It's going to tell you the standard error. It's going to tell you the test statistic, and you're going to have to decide based on that whether or not this was significant. Well, we knew we needed an alpha of 0.05. Okay, we knew we were dealing with a two-tailed test. We did not get anything that would cause us to reject the null hypothesis.
So I know you keep saying we've got to determine whether we're using a one-tail or two-tail test. When I read an example like this, I think one-tail. And so I'm thinking, like you had said, who's going to complain that the golf balls are going higher than 295?
PGA. Can't use them.
PGA. Yeah.
Really?
Yeah. Then they could make golf balls that would go
A guy
300-400 yards.
golf.
I actually heard here has some in fact.
Awesome.
300 yards. What?
It's filled with nitrogen.
Yeah. You should, like one of those super balls that bounce for that one. So again, this was sort of given to us. It was two-tailed, right? If you read this, assuming sample, blah, 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 perform a hypothesis test, the 0.05 level of significance, determine whether the manufacturer's process is controlled. Well, it wasn't all that obvious whether or not we were doing a one-tail or a two-tailed test, but in the heading it said two-tailed tests.
Right. Here, but if we're given a test or a quiz,
It's going to be obvious. It'll be more obvious. Okay. Again, most of the statistical tests, I'm not saying all of them. I know in this class we're going to do some, upper and lower tail tests, but I honestly don't run, upper and lower tail tests. We almost always just set the null hypothesis out there, and we reject it if you get anything on either side of it.
and so you double the minimum on the one tail to get the double tail.
Yeah, I know that's kind of goofy, and what does that really mean? Why are we doing that? Why is the formula that?
You see the same percentage on each side.
Yeah.
It's not that you're not splitting it and splitting. The p-value doesn't get shared between both sides. You have the same p-value on both sides. So you combine two double.
But your alpha is cut half. So if your alpha is 5%, you're cutting half to the right.
Yeah. I know it's odd to see because you think, wait a minute, when I split this up, I'm actually putting half here and half here. Why am I multiplying that by 2? and again, I don't know if I do a very good job of explaining this. It's just the fact that you are cutting it in half, and when you actually want to report it here, given that it's a two-tailed test, we have to take the minimum of this, right? You couldn't take this one, multiply that by 2. That's beyond the probability here, right? Because we don't really know what this is a generic, template here. So the p-value of the two-tailed test, unfortunately, yeah, that's just the way it is. Okay. But if you set your template up and you use this template and you save it, you're going to be able to use it in future problems. So let me do, so I don't really screw you up here for the next class and homework, I want to show you one more thing. Here's some explanation. Here's the confidence interval. Here's the t-test. I was going to get through this, but it's the same concept here, right? Instead of z, now we have a t-distribution. Why do we have a t-distribution? Well, we don't know the population standard deviation. We just don't know, right? All these other problems along, everybody's asking, well, why do you happen to know the population mean? Why do you know the population standard deviation? In the real world, you don't, okay? And then, if you don't know it, you use what's called the t-test. It's in your textbook in the appendix. It's very similar to the z-test, except that the area is to the right of the line, not to the left of the line. But look at this. This is almost identical to what we've been doing. We take a difference in some observed mean versus the hypothesized mean, and then we're dividing that by the standard error, which is what? It's the sample standard deviation divided by the square root of n, just like we've been doing before. But since we don't have the population standard deviation, we use the sample standard deviation. Is it different? Yeah. But so are these t-values, right? We sort of adjusted these t-values. They're not the same as the z-value. Conceptually, they're the same, but they're a slightly different value, and it's reflecting the fact that we're dealing with a sample standard deviation. And everything else is the same, okay? This accepting and rejecting, you come up with your alpha value, and if you get a p-value that's less than that, you reject it, right? We set up the null or alternative hypotheses the same, right? For one-tailed, lower and upper test, and for a two-tailed test, it's just that we're now using t's rather than the z values, like that. Okay, so it's really identical, except we have a different distribution rather than a z distribution. We have these t distributions. So here's the sample problem. So let me get you through it so you can see it here. We rated airports right on a 10-point scale. So Heathrow comes out. Let me put my, I'll give you guys a chance to read it. I'll draw my little curve. Okay, so we do not know the populations, but we do know the sample standard deviation is 1.052. We know our alpha value, right? Our alpha value equals 0.05. And so we now sort of have this, the basis to actually conduct our test here. Now, again, how do I know this is a one-tailed test? Well, again, just read the problem, right? We're trying to figure out if Heathrow is good enough. Are they really out here in this tail? Right? We're not assuming they're down here in a terrible airport, right? We're asking the question: is their rating high enough to really put them up here? So this is sort of an obvious and one-tailed test. And again, how do you set it up? Well, again, think of the area of the rejection that we're trying to prove. We're really trying to prove or show, is this observation way out here in the tail, is it significant enough? So I know the alternative is going to be this, that the inequality is pointing to the tail of the test. It's going to make this decision for us. So the null hypothesis is just the opposite. We're going to compute the value of the t statistic, just like we did before, right? The same exact concepts here, the mean minus the hypothesized mean. We're going to divide that by the standard deviation, this time of the sample, divided by the square root of n. So we get a t statistic of our t-value equals, what is it, 1.84? So we know that we are out here 1.84 standard errors from the mean. And the question is that significantly different? Well, how do we do that? With Excel, we can simply you can use your t-tables that's in your text. And if you guys actually have an older version of this slide, I just got rid of this using the tables, okay? You can use it. I had an example here. I just got rid of it just so we just have one way of doing it. We'll use the t.distribution.right tail, okay? If you do that in Excel, you type those numbers in Excel, those parameters, the answer you will get is a p-value, and it's 0.0354. So is that, and I'm sorry, the degrees of freedom is 59. And what is that? Degrees of freedom is 1 minus your sample size. We sampled 60. Isn't that what we did in this? A sample of 60. So our degrees of freedom happens to be 1 less than the sample size, which is typically the case. Okay, so we're basically going to type this into Excel, t.dis.rightTail. We enter the 184 as our test statistic. And 59 degrees of freedom, we got a p-value of 0.0354. So is that significant? Or not?
Yes.
Yes. So we can now claim that Heathrow, in fact, we have data to show that the scores at Heathrow are better than the average airport. So we reject. Right. We are going to reject the null hypothesis because we set up our alternative. Right. We sort of knew that we're pointing at the tail, so we set up this null as that our I want to write this carefully. I don't want to screw up the formulation, but that our 7 and this, remember, the less than or equal to, the equality always goes in the null. So we are going to reject this. We're going to accept the alternative hypothesis that we got a mean greater than 7. So again, this was what we were out to prove, right? We were out to sort of prove, we were hoping, I hate to say hoping, but we're out to prove that we have data that suggests that the mean is better than 7. That's our research hypothesis, our alternative hypothesis. Again, I looked at it because, well, I knew that we're really worrying about information out here in the right tail, so the alternative inequality is pointing in the direction of the tail of interest. Okay? So this would be how to look up that p-value of 0.0354. And we confront it, right? We can compare the p-value to our confidence level. It's less than that, so we got a very unlikely occurrence, not due to chance. It's due to the fact that Heathrow is in fact better than the average airport, right? It's not due to some random chance here. Again, if you want to do the critical value approach, again, same thing. Just like we did in the norm.dis with the t, we have this inverse. Okay, so we can type in this formula and the parameters it asks for, right, are the sort of the confidence level here and your degrees of freedom, and it would give you this critical value. And our critical value turns out to be 1.67. And what did we get? Our critical value, 1.84.
So,
and again, why this is, let me just try to explain that. Why is this 0.095 when you're out here? The weird thing about the t distribution is, if you look in your textbook, this is what t is giving you. It's giving you to the right of the critical value, whereas z was always giving you the area to the left of the critical value. I don't know why it's like that. It just is. Okay? Just happens to be like that. So if you would enter this formula in, right, you want to be, you're looking for this notion where, right, where you know, where you get 5% or 95%, 59 is degrees of freedom, and that's what you should get. So in either case, whether you're doing p-value or a critical value, again, it's one and the same, you would accept the alternative. You would reject the null and accept the alternative hypothesis. So I know we're almost out of time. Let me at least do this for you. Okay, I want to make sure you have these templates. You're going to have at least 2 templates before we go. So here's a two-tailed test where we have unknown standard deviation. So let's open up this orders data set, and we'll actually do it. Orders. I'll just go right to my. I'll just go right to the template I completed. Just go through it for you. The sample size again. Count A:(A), right? We're going to take this entire column, whatever's in it, and because we said count, it's only going to count numbers. So you're okay to have that units heading there. The sample mean, yeah, there's the formula for the sample mean. It's equal average, and then bingo, the whole column, right? You have to paint up the whole column here just by clicking on the A. Sample standard deviation. Okay, there's a formula. It's the standard deviation dot sample. Again, it's the entire column, so it's A:(A). The hypothesized value. Again, I shaded this in green. For me, it's a reminder that I have to enter a number there. Right? Even if whatever I put into the Excel spreadsheet here for data, I'm still going to have to go back and give it some kind of a hypothesized value here. So that turns out to be 40. So I shaded that green as a reminder. This time I remembered barely. Standard error. Yeah, there should be no surprise what this formula is. We took the sample standard deviation and divided it by the square root of n. Just like we've been doing all along. Right? We took the sample standard deviation and we divided it by the square root of n. And this is our standard error. Test statistic, it'd be very similar, right? Just like we've been doing before. We have some observed mean, which is our sample mean. From that, we subtract the hypothesized mean, and we divide that by the standard error. Okay? And we get the value of the test statistic. Degrees of freedom, yeah, how did I get that? Yeah, it's the sample size minus 1. Degrees of freedom isn't always going to be that, but for most of these kinds of problems where you have one set of data, one column, right, it's going to always be that. It's going to be n minus 1, right? The sample size minus 1. Then the lower tail test. Okay. Equals t dot distribution. We put in the test statistic, comma, degrees of freedom. Right? This is the difference in this t distribution. All you need is a test statistic and the degrees of freedom, and you will get the value that you seek. Okay, upper tail is just 1 minus that. And again, this notion of the p-value of the two-tailed test, that'd be a good one that'd be a good question to ask Matt. Why is that 2 times that? Okay? Again, you've got 2 of the 3 templates I wanted to give you. Shit, I don't know how else to give you the 3rd one. I guess I could just email it to you rather than go through it. I could put it up here, but class time is coming to an end.
Which data file is it? So it's
Women's golf.
just knowing that. Women's golf.
It's women's golf. So let's see if we have that. Now, again, I know I'm shortchanging you here. You know, you got the midterm coming up. I don't want to screw you up with not having these templates. I know I haven't maybe explained them well enough, but yeah, at least you'll have them coming in. You get a chance to visit with Matt. I don't want to not get through some of the more important things. Once again, the same comments that I have all along here. Okay, I would put them in the same places. I may have moved the rows around a little bit from where we started, but I highlighted these 2 cells. Again, this is what you're going to have to change, but the rest of these contain formulas that are going to be fine regardless of the data. But remember, this is a hypothesis test about a population proportion. So we're going to have some kind of qualitative data here. It's going to be yes, no, male, female, something like that, okay? Some binary variable is going to be in column A.
On the sample size, probably couldn't be the whole column, right? With golf for female.
They came to account A.
That's one.
Yeah, I did. Yeah. Again, I'm not sure what they told you in your textbook, but that's what I did. It's the entire column, but because we're going to have some label up there for the heading, right? I just said it's count -1. So we're going to not count the heading. Okay. The reason we didn't have to do that before is we're dealing with numbers, and the count knew to ignore numbers. But now I have count A, right? So it's counting non-blank cells. And then it's subtracting 1 to get rid of the header that says golfer. Okay? Then our response variable, again, was about females. So I just said female. And honestly, I mean, if I type that with a lowercase f, that's fine too. I don't think Excel worries about the actual case when it makes the comparisons. So you could say, you know, lowercase f. I just did it because to be consistent. So our count of response for that formula okay, here's what I did. Again, I did the entire column, didn't worry about golfer up there as the label. And I said, it's count if. I did a count if, and I told it, look at the entire column, and then my criteria, I pointed to the cell, the response variable cell. Okay? So I said, right, that's a count if, like the counter column if the criteria is female. So I just pointed to whatever the response variable was. Female. Sample proportion, there's a nice formula. Again, should be straightforward, you guys. What is it? It's the count of our response, P5, divided by the sample size. Right? So this is telling us that if we take all the 400, and we got 100 females in our sample, it's 25% of our sample proportion. Right? That should sort of be obvious from the results here, right? Our sample size was 400. Our count of female responses was 100. Therefore, our sample proportion is 25. The hypothesized value, again, you have to determine what the problem is asking you. If you go back to the problem, it was actually asking us whether or not, I think we got more than 20% women in this golf sample. So that was a hypothesized value. So I had to enter that, not a formula. The standard error, yeah, this should be really no surprise here. What is this formula? Actually, remember this was the P times 1 minus P, right? Remember the standard error for proportion. P times 1 minus P divided by D3, which is the sample size. And then the whole thing was the square root, right? So this was the sample size, and then that was the formula, right? This is the formula I put in that cell, right? Remember this? We have this on the slide. This is how we call this? This is the sample standard error, the proportion, standard error of the proportion.
Can I ask you?
Yeah.
This goes way back, sorry. I wasn't able to count anything in A. Is there something that you think I'm doing?
It's to use the formula count A.
Count A instead of just count.
The actual formula is count. I'm sorry, count.
Gotcha.
Count A.
Okay.
Right. It's not just count. It was count A, and if you remember count A, it counts non-blank cells. And I had to subtract the 1 because I used the heading of golfer. It would have counted golfer. So it did count golfer, and I just said, okay, let's just subtract 1. So we always have a heading in there, in other words. It's okay to always have a heading. In fact, you need a heading in there. Okay, so where were we with Z-stat? Well, let's go back to standard error. Remember, if you go back to the notes, this is the standard error of the proportion, right? The formula, we have many slides with this. Well, what is it? There it is. It's the square root of, and then just sort of follow it through. Let me highlight it. It makes it easy to see here. Right? We took the square root over all of this of D8, right, times 1 minus D8. That's what I got over here. P times 1 minus P divided by N, right? N being the, being D3, N being the sample size. And then we took the whole thing as the square root of that, and that gave us the population. That gave us the standard error of the population proportion. The test statistic, and very straightforward. The test statistic, what is that? Just like we've been doing before, right? We take the sample minus the hypothesized mean, right? This is our sample mean, or our sample proportion. From that, we subtract the hypothesized mean. What do we divide it by? The standard error. Okay, just like we've been doing in the other templates all along. And so we got a test statistic of 2.5. That's going to be significant in most worlds. Again, one-tailed lower, one-tailed upper, et cetera, or the two-tailed test. I'm not sure what we're doing in this particular test. What was it? Let's go back to the slides. It doesn't matter. We have all 3 values here, and you just have to read the problem and figure out what were we doing here. I think it was actually a one-tailed. I thought it was a one-tailed upper tail test. Let's just see. Determine whether the promotion has increased women players. Okay? So again, we're trying to figure that out, whether or not it's increased the proportion of women players. So before this proportion was 0.20, and we're trying to figure out whether or not we're now up here. Okay? So this is in fact a one-tailed test. And again, to do the template, you don't even have to worry about this. Right? This is a one-tailed, because we're going to get all 3 measures reported. But what are we really interested in? Yeah, we're interested in this upper tail, right? Did that treatment, right, did it actually increase the number of female golfers? So we're going to say, yes if we get some value up here. So our null hypothesis would be just like this. Note that it did not increase it. Note that the average is 0.20, and the alternative is it is greater than 0.20. So what did we discover? Well, since we're doing an upper tail test, we discovered that the probability of getting this result by chance alone is 0.006. So it must be due to whatever this golf company was doing to attract female golf players, right? It didn't happen by chance alone. We would reject the null hypothesis, right? This would be true. We have evidence to prove that our mean is in fact greater than 20%. So we reject the null, we accept the alternative hypothesis. I apologize, keeping you guys here beyond this, because, but I just want to make sure you had what you needed if you wanted to, for some reason, start the midterm tonight, right? We can finish this up tomorrow.
Which one?
I'm sorry, last one. Again, this is a question you're going to ask Matt. Why do we multiply that by 2?
I think I figured that out. So the 2 tests, you're taking, if your alpha is 5, so yours is 5.05. For the 2 tests, you have 2.25 on each side. So instead of trying to compare the 2-tailed p-value and lower than 0.25, you just double it and take an equivalency. Does that make sense?
Yes.
You're artificially doubling it just so that it shows that it's significant compared to
Yeah, you actually, the other way of thinking, because you have a 2-tailed test, right, you have half as much significance in either tail. Okay, so that's why we're sort of, doubling this, if you will, the p-value from the, from the 1-tailed to the 2-tailed test. But again, it's just a template, right? I just want to make sure you got it. And why don't we just do this? Now that you have it, I'll come back tomorrow, and if you feel like rushing these last slides too quickly just to give you the templates, we'll go back and do them. If not, we'll start new material. Okay? So let's stop there. I'll leave this up here. In fact, if anybody didn't get these and you really want them, how about if I just leave them here? Is that all right? Leave them on the desktop?
Oh yeah, that's a good idea.
Okay? So remember what they were. This is women's golf. Like, I can even leave them running, I guess. I'll just save them up here. How about if I do that? I'll just rip these things out. Here's women's golf. And what was the other one that we did? Orders? Yep.
And golf tests.
Oh, I know the problem.
Yes.
Can you see if you have access to the Google Calendar? Because I put all the stuff on the Google Calendar, almost. I have to put one more thing on there. So how do we all have access to it?
Well, let me turn this off.
Sorry.